Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we start going into derivatives of trigonometric functions, as you can see on the screen. But we're going to start with a tale of two lemmas. Now, before I get into the actual lemmas themselves, let me just discuss what the difference is between a theorem and a lemma. So a theorem is basically a major statement, like the Pythagorean theorem is a major statement in mathematics. Now, not all theorems have to be massively important, but most of them are. And then after you have a theorem, you might actually have a sub-theorem, something that kind of dovetails off of that, and that is called a corollary. Generally speaking, corollaries are so kind of obvious from a base theorem that they generally don't need proofs in and of themselves, although you can prove corollaries, don't get me wrong. But in general, there's almost always very just obvious from the statement of a theorem. As a simple example, the theorem could be the Pythagorean theorem, and a corollary could be there exists a right triangle with sides 3, 4, 5. That is true because, well, with 5 being the hypotenuse, that is true because of the Pythagorean theorem. That's a corollary, and there's no real need to mention that as its own little theorem. That would be a ridiculous little theorem to mention. Now, the thing that we're going to be dealing with in this video is a lemma. And a lemma is often used within a theorem. It's basically a sub-theorem of a theorem. So when you go to prove actually, I should say a lemma is really a sub-theorem used within the proof of a theorem. So for example, if you're going to prove the Pythagorean theorem, you might, maybe in one of the many proofs of the Pythagorean theorem, you might need a lemma stating that the sum of the angles of a right triangle have to be 180 degrees. Well, I'm not saying that that's an actual lemma to prove the Pythagorean theorem, but the idea is that you are in the middle of a proof for a big theorem and you need a little extra piece of power to help you prove that, and that extra piece of power is usually some type of sub-theorem that we would call a lemma. So with that distinction being made, this video is focusing on two sub-theorems that are going to be used to prove a major theorem. And the two sub-theorems that we're going to be dealing with here are actually in and of their own right very powerful theorems to help us evaluate limits. So here's the first one. The limit as theta approaches 0 of sine of theta over theta is equal to 1. And you should be strongly familiar with trigonometric functions at this point, so I don't need to tell you what the sine function is. And the proof of this is actually such a gorgeous proof that I really want to spend some time on it here. This whole video is really dedicated to the proof of this lemma, which I titled a theorem, by the way. It's okay for me to call it a theorem. It is technically. And then we'll prove a different lemma right after this. Now we're going to start the proof by first drawing a circle, and I just put on a coordinate system here where we have the x-axis and the y-axis. And I drew a ray or a line, blue line, going through the origin and intersecting the circle, the unit circle, that circle in green there. I didn't finish out the circle because I don't need the other quadrants for this proof. And the angle that our blue line there makes with the x-axis, we'll call that angle theta. This allows us to start talking about theta because we want to compare the sine of theta to theta itself. All right, there are a couple other things I want to do here. I want to draw a vertical line from the, or an altitude, I should say, from the intersection of the blue line and this unit circle. So let me go ahead and do that. And actually, maybe before I do that, I should just go ahead and make a couple mentions here that are relevant to the point that we're at right now. So you notice I labeled things O for origin, put a little dot there, A for the intersection with the x-axis for the unit circle, and B where those the unit circle intersects the blue line. All right, so by definition, the length of the arc from A to B is equal to theta. That's actually by definition of really the unit circle definition of trigonometric functions, honestly, but it's a definition of a radian. And maybe I should write that off to the side just to really remind you. So recall from your trig course that the arc length S is equal to the radius of the circle times the angle that gets cut out by that arc. So if we call this arc length right here S, and by the way, when I say this arc length, I mean this arc length. If I call that arc length S, then that length should be the same as the product of the radius of this green circle and the angle that we're cutting out. Well, the radius of this green circle is 1. It's the unit circle. So I know that the arc length is going to be theta. So I'll write that in here. So since radius is 1, arc length is theta. And that just gets us back to this statement here. The arc length from A to B is theta, just by definition. Now notice that I've drawn in the altitude here. The altitude, by the way, makes a right angle with the x-axis. And I've also drawn in a brown chord, is what we'd call that, between A and B. So that chord is just a direct distance between the points A and B. All right. So something we should note here, the length, oh, I should probably also note, let me use black for this. I'll go ahead and call this point right here C. We don't know what that point is. It doesn't really matter. Actually, we kind of do know what that point is, but let's just say it doesn't matter right now. So note, the length of the chord from B to C, and by the way, I shouldn't say length of chord, I should say the length of the altitude from B to C. So I'm talking about this length right here. That length, because it's a directed altitude, should be less than the length from A to B, this length right here, because that's a hypotenuse of an actual right triangle. If you look at it, there's actually a right triangle right here with side lengths AC and BC and hypotenuse AB. And just from geometry, we know that the length of the chord AB, or the hypotenuse AB, will be less than the length of the altitude BC. So let me write that in. So the length of BC should be strictly less than the length from A to B. However, that chord length, as we know also from our geometry, that chord length will be less than the arc length from A to B. Let me highlight that if I can. My highlighter's kind of large, but that arc length is going to be longer than the chord length between A and B. And that's just because, well, this is from geometry, from our geometry prerequisite. So I'm just going to go ahead and make that statement here. So this chord length from A to B is less than the arc length from A to B, and I'll denote that with a little curvy top on it. Now, all that should be logically sensical. Like, we should know that's true. We've also stated, just from by definition, that the arc length A to B is actually theta. Okay, so here's where I'm going to relate sine of theta to theta. Notice that I have a blue right triangle, well, almost all blue. It's not all blue, but here I can draw this in. So now I have a blue right triangle, right? And the sine of this theta right here is opposite over hypotenuse. But this hypotenuse is actually a radius of the unit circle. This hypotenuse is of length 1. So really the sine is just the opposite over 1, or in other words, the length from B to C divided by 1. So I'm going to go ahead and write that down below. The sine of theta is just the length from B to C. Technically, to be honest with you, it's the length of BC over the hypotenuse, but the hypotenuse is of length 1. Great. So what does this mean? Well, this implies that sine of theta has to be less than theta. And why do I say that? Because sine of theta is equal to, let me get the right highlighter, BC. But BC is less than theta. So if sine of theta is equal to BC and BC is less than theta, then sine of theta must be less than theta. That is pretty nice. But that doesn't give us the entire proof. That just gets us a relationship between sine of theta and theta. We have a little more work to do here. So let me zoom out again. And here's where the proof gets a little bit busy. As you can see, I've drawn a tangent line in here. In fact, let me go ahead and just tell you, this is a tangent line, right? Tangent line at, oops, I was kind of mixing my words there. Tangent line at B. That's our tangent line at the point B on the curve. And I'm going to be using that along with an altitude from point A back up to the blue line. So this is going to look really busy. I apologize. There we have it. So I've drawn in an altitude from A to this point D up here, and I've labeled that point obviously D, and I've also labeled the intersection of our tangent line and that altitude as E. Now it does look really terrible. I 100% agree with you, but this just allows us to solidify our proof. So watch what happens. From our geometry, and this is kind of the most hardcore geometric proof that you'll see in Calc 1, that it relies so much upon your geometry prereqs, and so people tend to get kind of intimidated by this proof, but it's actually really kind of a wonderful proof. But from our geometry, we know that the length, the circumference of a circle inscribed in a polygon is going to be less than the side length of the polygon itself. So therefore, the length of this arc from A to B, the length of the arc from A to B here, is going to be less than the length of the line from A to E plus the length of the line from E to B. Again, the length of the arc is less than the length of those two black lines, I guess you could call them. And so I'll write that down below here, give myself some room. So there I've written it in notation that the arc length from A to B, is less than the sum of the line segments BE to AE. So again, arc length, green arc length from AB is less than the line segment summation AE to BE. So there we have our statement. The arc length from A to B is less than the line segment lengths BE plus AE. So let me just again showcase that. The chord length, or arc length from A to B there, not chord length, but green arc length, is definitely less than the summation of the line segments BE plus AE. However, you can actually see it even here, but it's true from geometry as well, that BE plus AE, that's less than AD. That length, so this length plus this length, is less than this full length right here. And the reason why that's true, actually, I don't need to actually just cite, oh, it's true because of geometry. It is true because this is a right angle right there, and so therefore this is a right angle, and this side would be the hypotenuse of that right triangle. So if you're really thinking about it logically, you have this distance AE plus this distance BE. Well, this distance AE plus this other distance DE should be larger. They share the same AE distance, but the DE is the hypotenuse of that right triangle involving B and E. And so therefore, the distance from A to D is actually greater than the distance from A to D is actually greater than AE plus BE. That's a mouthful. I just said right there, it's quite a bit, but It is true. If you just look at the geometry of the figure, you can easily see that the arc length from A to B is definitely less than the chord length from A to D. But we said something about the arc length of A to B before. It is equal to theta. So I'll just go ahead and write that in. So this arc length right here is just equal to theta. The length A to D, well, this will take some highlighting just so you could kind of ferret out what it is. There's a right triangle right here. There we go. That's a right triangle. And I'd like to somehow relate a trigonometric function of theta to this triangle. Now, I don't want to use the sine. The reason why I don't want to use the sine is because the sine of theta would be this length A to D, which is kind of what we want. But then it would be more than, the hypotenuse would be longer than 1. And I just don't want to do that. I would like to involve the unit circle in my statement. But if you look at this distance right here, that distance is also a length of 1. And that is the horizontal leg of this right triangle. And so if I want to relate that horizontal leg of the right triangle to this highlighted side right here, then I can go ahead and use a tangent. So I could say the tangent of theta should equal the the distance A to D divided by 1, right? It's opposite over adjacent. So really, that distance AD is just the tangent of theta. And let me scroll down and show you, we actually have that distance AD in this inequality, and now we know that's just going to be the tangent of theta. Thus, theta must be less than the tangent of theta. Well, that's pretty good, I guess. And let's see what we could do here. Let's go ahead and multiply both sides by cosine and divide both sides by theta. We're in quadrant 1, so there's no reason for these things to be negative. So if I multiply both sides by cosine of theta and divide both sides by sine of theta, I get the following. And now I have an inequality that I want to work with. When we got to this point way up here, I could have said, you know what, let's go ahead and divide both sides by theta to get sine of theta. Whoops, that's not sine of theta. This is sine of theta over theta is less than 1. Again, our angle's in quadrant 1 for this argument, and so therefore I'm not really dividing by a negative number. And now we have this beautiful triple-sided inequality. And you better believe it, we're going to use the squeeze theorem. The limit as theta goes to 0 of the cosine of theta, we know that's going to be 1. And the limit as theta tends to 0 of 1 is equal to 1. Thus, the limit as theta goes to 0 of that central expression must also be 1 by the squeeze theorem. And that is a proof of this theorem way up at the top. It is not an easy proof for a lot of people to follow, but it's a beautiful geometric proof. It's just, I love the fact that you get to use geometry in your calculus course, and I just think it's a gorgeous proof. We're done with that proof, so I'll write QED, quod erat demonstratum, so it has been demonstrated. And this video is called A Tale of Two Lemmas because we have another lemma to prove, but it's going to be a short proof. So let me go ahead and show you the other lemma. This is the theorem that as theta tends to 0, cosine of theta minus 1 over theta is equal to 0. So remember, the sine of theta over theta approached 1 as theta was approaching 0. The cosine of theta minus 1 over theta is approaching 0 as theta approaches 0. And this proof actually is pretty nice. It's not terrible. So let's just take the limit as theta goes to 0 of that cosine of theta minus 1 all over theta. What we're going to do is, that's where we're starting. We're going to go ahead and multiply numerator and denominator by the conjugate of the numerator. And that's because with trig functions, sometimes conjugates can be very powerful. So I'm going to zoom in here, and I'm going to multiply top and bottom by the conjugate of the cosine of theta minus 1, which would be the cosine of theta plus 1. And as I usually say, I will not multiply out that denominator unless I really, really have to, but I don't want to, so I'm not going to. But the numerator will multiply out beautifully. This will be the limit as theta is approaching 0 of the numerator becomes a cosine squared of theta minus 1 all over, again, theta times cosine of theta plus 1. That's not too bad. And you happen to know that 1 minus cosine squared would be a sine squared. So cosine squared minus 1 would be a negative sine squared. So I'm going to write this as a negative limit as theta approaches 0 of sine squared of theta over theta times the quantity cosine of theta plus 1. Now, this is an interesting lemma. It's more of a corollary, actually. It's sort of a result of the previous theorem that we did, but it's not super obvious, so I wouldn't actually call it a lemma. So this is going to be the negative, and now I'm going to break this limit into the product of two limits and cross my fingers and hope that each of these factors in this product will exist. Because if they don't, you're always allowed to try this. And if one of the splits does not exist, then you have to glue it back together and start all over. So let's see what happens. Oh, something looks strongly familiar. Not strangely, but strongly. That is 1. We just proved that the limit as theta goes to 0 of sine of theta over theta is equal to 1. So that limit will turn into 1 with a negative in front of it. And let's see, what is this guy right here? As theta goes to 0, the numerator tends to 0. Let's see if we could just use direct substitution, right? The numerator tends to 0, and the denominator actually tends to 1 plus 1, or 2. Yep, we could totally use direct substitution here. So this is going to be 0 as the other limit. And of course, negative 1 times 0 is 0. And there we have proved that the limit as theta goes to 0 of cosine of theta minus 1 over theta is equal to 0. QED. That was a lot faster because we got to use the fact that the limit as theta goes to 0 of sine of theta over theta is equal to 1. Now, some people would say, oh, so therefore that theorem we just proved is actually a lemma for this theorem. And in a way, it kind of is. We needed that information to allow us to trade this highlighted picture out for a 1. If something's called a lemma, it's not always a lemma. It might be a theorem as well. Not that big of a deal, but interesting enough.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.